Hello grade 11s, this is physical science and my name is Gillian. We are busy with redox reactions, and so we're going to have a look at consolidating our knowledge. How do we use oxidation numbers to figure out what is oxidation and what is reduction, and then what do we do with that? So let's have a look at the overview to remind ourselves where redox reactions fit in. So redox reactions, we need to be able to work out the oxidation numbers to tell whether oxidation is happening or reduction. You can use the periodic table, or we can learn the whole list of rules that go along with figuring out the oxidation numbers. Redox reactions, what do they comprise? They comprise oxidation, and that is where electrons are given away for the substance to become more positive or for the oxidation number to increase. That aids reduction, and so it is then called a reducing agent. The reduction half reaction is the substance that takes on those electrons that are given away, and in so doing aid oxidation, and so they are the oxidizing agent. Now, this standard reductions potentials table is important for us to understand and to use, and we need to know how to use it properly. So that's what we're going to focus on today. The standard reduction potentials table is a list of reactions, and they have been placed in a very special order. And the reason why they've been placed in an order is because not every substance is the same. They're all different, and they all behave differently. And so they will have a different reactivity. So the one element will react in a different way to the next one. And I want to show you the basic principle behind this reactivity series. If we look at displacement reactions, we can see that the negative ions are replaced. They're swapped out as they join onto a positive ion. So let's have a look at the screen, and we can see that I've got magnesium metal here. It's a solid, and zinc chloride, which is a compound, and it would be placed in solution to form zinc 2+ ions and 2 chloride minus ions. Okay, so it's dissociating. It's called dissociation. Now, what happens is that this chloride ion is swapped out and joins on to the magnesium metal. What we are left with is the zinc. We can see there that this could be a redox reaction. So let's check if it is. So magnesium, I'm going to change the color of my pen so we can see the difference. Magnesium as a neutral or pure substance would have an oxidation number, a unit oxidation number of 0. Magnesium in magnesium chloride, let's have a look. We're going to draw a line through like that. The chloride is in group 17, and so it's going to have a unit charge of minus. There are 2 of them, so that's 2 minus, and so magnesium is going to be 2+. There we go. So can we see that there is a change in oxidation number from magnesium as a solid, as a pure element, to magnesium 2+ in this compound? We would expect then that the zinc would also change. Let's just go back to the magnesium for a moment. So if it's going from 0 to 2+, then it must be giving electrons away, and that must be giving 2 electrons away. So it gives 2 electrons away. So that is going to be the oxidation half reaction. Now, with the zinc starts off in this compound as zinc 2 plus. What does it end up as? It ends up as zinc 0 because it is a pure substance and pure element. And so on this side, we're going from zinc 2 plus to 0. What's happening there? Well, zinc 2 plus, the ion is taking on 2 electrons, so it is becoming more negative, and so that must be reduction. So here is reduction, and this is oxidation. Okay. When we have a look at other displacement reactions, let's say we put zinc metal into the test tube and we have got magnesium chloride in the aqueous solution. Guess what? Nothing happens. You can see the cross there. Nothing happens. So when we experiment with these different displacement reactions, we find that some substances are not able to displace the metal. So magnesium is strong enough to displace the zinc from the zinc chloride, but zinc is not strong enough to displace the magnesium from the magnesium chloride. And so we get a sense that we have got stronger reducing agents, in other words, those that are taking that are going through oxidation. So those substances that are oxidizing are reducing agents. We get a sense that we have got much stronger ones, and that there is a scale, and they then go right down to the bottom of the scale where they are the least oxidizing agents in strength. So this is what our standard reduction potentials table is made up of. All these half reactions that are graded according to the strength of the reducing potential. Later on, instead of using these displacement reactions, the chemists started using electrochemistry, which then electrochemical cells, which then gave them a more accurate reading. So let's have a look at these tables. Well, there are two, and what they can do for us. So there are two that you'll find on your data sheet. One is the 4A, and the other one is the 4B. So the 4A has got the weakest reducing agents at the top, and then the strongest one at the bottom. The 4B is flipped around, where you've got the strongest reducing agent at the top and the weakest at the bottom. Now that's the one that I like to use. So you need to decide which one are you going to use, and you stick to it. You don't change, you choose one. So because the substances behave very differently, their reactivity is going to be different, and so that is why we have this table. It's graded from the most reactive to the least reactive. Then on this table, you'll see that there is a double arrow on these reactions. We're going to have a look at it in a moment. And that means that you can read this reaction from either way. You can read it from left to right, or you can read it from right to left, depending on what is happening. So if you're reading it from left to right, it is the reduction reaction that you are reading. If you are reading it from right to left, you are reading the oxidation reaction. So that is what this double arrow means. Because of different situations and different reactions, a substance can either be oxidized in one situation, or it can be reduced in a different situation, a different reaction. And so that's why there is a double arrow. So we have here a question, and as we go through it, we're going to look and see how this table is used. Write a balanced redox reaction for the reaction of iron 2 ions with dichromate ions. So we've got iron 2, now that 2 is Roman numerals, and it means that the ion is of a 2 plus nature. And dichromate ion, so here's the dichromate ion, Cr2O7 2 minus. Now, it tells us the products. The products that are formed are the iron 3 plus ion, so there we go, I've placed it there. and the chromium 3 plus ion 3 over there, and so that's what it looks like. Let's check it out. We've got iron 2 plus, it becomes iron 3 plus. What is happening? Its oxidation number is becoming higher, it is becoming more positive, so it gives 1 electron away. What is happening to the chromium in this ion? So I'm going to change my pen so we can see the difference, and then we are going to divide it up. So I'm going to divide it up like that. I know that the overall charge on this ion is 2 minus. Can we see it there? 2 minus. So oxygen, from our knowledge of the periodic table, has an oxidation number, a unit oxidation number of 2 minus. There are 7 of them. So that means that there is going to be a charge of 14 minus. 7 times 2. Our overall charge has to be 2 minus. So on this side, we have to have, how many charges? We have to have 12 plus charges. There are 2 chromium sitting in that complex ion, and so we divide 12 by 2 and we get plus 6. Okay, so I've got an oxidation unit number of chromium of plus 6. It becomes 3 plus. What's happening? It is taking on electrons, and the electrons that it's taking on is 3, from 6 to 3, so we're going to put in a 3 electrons. Which one is being oxidized? Which one is being reduced? So this substance over here, the iron 2 plus, is being oxidized. Oxidized. How do I know? Let's go to that oil. Oxidation is loss. It's losing electrons. So what is this one going to be? This one is going to be, it is reduced. Reduced. Okay. What are we going to do with this information? We are going to write a balanced equation. We're going to use this table. So here I have a portion of this table. It's not the whole table. You can see here increasing, reducing ability. So in other words, the thing at the top over here is a strong reducing agent. The one at the bottom is weak. It's a weak reducing agent. I've already highlighted the 2 half reactions. So here it is here, iron 3 plus becoming iron 2 plus, if I read it from left to right. And this one over here is the dichromate ion becoming the chromium ion 3 plus. Okay, now the oxidation reaction we know is this one. We've already worked it out. So what am I going to do? I'm going to read it from right to left, and I write it like that. So I write it as Fe2 plus, you can see there, with a single arrow, one arrow, Fe3 plus, and 1 electron. I am going to read the the chromate ion to chromium ion from left to right. That's how I'm going to do it. And I'm going to write it like that. Okay, so I've written part of it here. It's the chromate ion, dichromate ion. Now I need to add in here 6 electrons, and I also need to add in here 14 H plus ion. Then I need to add in the 2 and plus 7 H2O, water. Okay, for this reaction to be balanced, the electrons have to balance. I see I've got 6 electrons here. I have only got 1 electron there. What am I going to do? I'm going to times by 6 all the way through this reaction. I'm going to change my pen quickly, and I'm going to get 6 Fe2 plus ions, arrow, 6 Fe3 plus ions, plus 6 electrons. Now I know that it is balanced. Because 6 electrons there and 6 electrons there, it is a balanced equation. I'm going to write these two together. I'm going to add them together. So I have 6 Fe2 plus ions plus my dichromate ion plus 14 hydrogen ions, arrow, to give me 6 Fe 3 plus ions plus 2 chromium ions plus 7 H2Os, 7 waters. Right, there we go. I have my balanced equation and all good to go. Grade 11s, we have run out of time. It has been great to have you with me. Hope to see you next time. Welcome back, grade 11s, from the break. Right, we are busy working with the standard potentials table, which is a whole lot of redox reactions that have been graded, put to scale according to their ability to reduce. So being a reducing agent. And the one that I'm using is the 4B, and it is from the most the strongest reducing agent to the weakest reducing agent. So these kind of questions or working with this table can only come right for you if you practice, and you need to practice questions. So we're going to go through another question, and we can get used to working out the oxidation numbers, and from there finding the oxidation half reaction, the reduction half reaction, and putting them together in a balanced equation. So the first question I have for you is the reaction between permanganate ion, there we go, there's the permanganate ion, and hydrogen sulfide is here. Okay, so we've got the manganate ions given to us in this reaction. They're plus hydrogen sulfide is Mn2 plus, and we get sulfur solid and we get water. So they are asking us in the first question to define reduction in terms of oxidation numbers. So let's think about what happens in reduction. Well, if we do this, RIG, oil rig. So rig is our reduction. R stands for reduction, I stands in, and G stands for gain. So reduction is gain. So reduction is gain. We're gaining electrons. What's going to happen to the oxidation numbers if there is a gain in electrons? So if we're gaining something negative, our oxidation number is going to drop. Our oxidation number is going to become less. It's going to become more negative. So define reduction in terms of oxidation numbers. Reduction is the decrease in oxidation number. You can also say it becomes more negative. What's our next question? Determine the oxidation number of manganese in the permanganate ion. Okay, so we are going to take this ion here, and we are going to work out the oxidation number, the unit oxidation number of manganese. So like we've done before, we're going to draw a line through it. We know that our overall charge here needs to be minus. Why do I know? Because there's the minus there. I'm going to swap over pens so we can see more clearly. Oxygen, according to our rules or the periodic table, is 2 minus. We have got 4 of them. So if we times it out, 2 times 4, we end up with 8 minus. My overall charge is minus. So to balance that out, I need to have 7 plus. There's only 1 manganese there, and so its oxidation number, the unit oxidation number of manganese, is going to be 7 plus. The next question, write down the formula of the substance that undergoes oxidation. So oxidation is what? Let's have a look at oil. So oxidation is loss. Oxidation is loss of electrons. So electrons are being given away. If we have a look at our equation, we see that manganese, we've already worked out, has got a 7 plus charge. Over here, it has a 2 plus charge. Is it giving electrons away? Is it becoming more positive? No, it is not, because it's going from 7 plus to 2 plus. So what else could we try? Well, we could try this gas, which is hydrogen sulfide. So let's have a look at it. We're going to put the cross through there. Sulfur, we're not sure about. Let's say we're not quite sure about sulfur. So hydrogen we know, because hydrogen is in group 1, hydrogen is going to give 1 electron away, and it is going to be plus 1. There are 2 hydrogens there. So overall it's going to be 2 plus. This is neutral, so the negative part has to be 2 minus. There's only 1 sulfur, so its unit oxidation number is 2 minus. What about sulfur on this side? Sulfur on this side is on its own. It's a pure substance, it's an element, and so its unit oxidation number is going to be 0. So sulfur in hydrogen sulfide is 2 minus, and it becomes 0. It becomes neutral, S0. Okay, so it is becoming less negative. Oxidation is loss in electrons. So the thing that is being oxidized is hydrogen sulfide. So we're going to write this down here, write down the formula of the substance that undergoes oxidation. It is H2S, hydrogen sulfide. Our next question is explain the answer in question 1.3 in terms of oxidation numbers. Well, what is happening? Sulfur in the hydrogen sulfide starts off as 2 minus. What happens to it? It ends up as with a unit oxidation number of 0. So the oxidation number of sulfur, we have to say, okay, it increases. And it increases from, what does it increase? It increases from 2 minus to 0. That's what's happening to the oxidation number. Now, write down the formula for the oxidizing agent. The oxidizing agent is that substance which aids oxidation by itself being reduced. We've already looked at that. We've seen that this permanganate ion, or the manganese in the permanganate ion, started off as 7 plus and it ended up as 2 plus. So what's happening? It's becoming less positive. It's becoming, it's reducing. The oxidation number is reducing. So that is the thing that is being reduced, the manganese in the permanganate ion, and so it is going to be the oxidizing agent. So we're going to write this down. It is MnO4 minus. That is the oxidizing agent. We want to move on. Write down the oxidation half reaction. So the oxidation half reaction, we have already seen that the sulfur is in the hydrogen sulfide is a thing that is being oxidized. So H2S becomes sulfur. What is it doing? It started off as 2 minus. I'm just going to write it up there. It ends up as 0. What is it doing? It's giving away 2 electrons. So plus 2 electrons. Now, the important part, this is the important part. Use the ion electron method to write down a balanced net ionic equation. So net means the end, right? The overall. Ionic is where we speak about the ions. So sometimes things are in compounds, and we have what is called spectator ions. They don't participate in the reaction, the redox reaction, and so to make it simpler for us, we leave those out. So when we're speaking about the ionic equation, we're talking about only the ions that participate in the redox reaction, receiving electrons or giving electrons away. So I'm going to take us back to the 4A table that we used earlier. Oops, I've skipped it. There we go. And I've highlighted these 2 reactions in yellow. I know this page is pretty full, but if you could put your eyes towards these yellow ones. So here is the one reaction. Oops, let's go back to that. So here's the one reaction over there. Here's the other reaction over here. Can we remember which way we're going to read them? Oxidation we're going to read from right to left. Right to left. Oxidation, and here's our oxidation reaction. We read it from right to left. I'm not winning with this today. Let's see. Right to left. Our reduction reaction, we read from left to right. So that way there. So I'm going to write down the oxidation half reaction. Let's see if I can remember. We get 2H plus, 2 electrons, and a sulfur. So let's write that down. Okay, so H2S, hydrogen sulfide, sulfur plus 2 electrons plus 2H plus. Okay, if you can, you need to try and put in the phases of the components. Okay, our next equation, half equation, is with our permanganate ion, and you can see it over there. So we're going to read it from left to right, and it's 8 H plus 5 electrons to give us 4 water. So let's write that one down, and we have MnO4 minus, it's aqueous, aqueous, plus 8H plus electrons. I can't remember, we're going to have to go back to that. And what's that going to give us? Mn2 plus in the aqueous form. And I think we had 4 waters. Let's just check how many electrons those are, just making sure. I've gone past it again, there we go. Okay, how many electrons? 14H plus and 8H plus and 5 electrons. Okay, 5 electrons. So let's get there. 5 electrons. Now, for this reaction, this reaction to be balanced, we need to balance out the electrons. It's the electron transfer, which is the thing that needs to be balanced. And we can see that we've only got 2 here, 2 electrons, and we've got 5 here. So we need to work out what we can times these by to come up with the same number of electrons. So if we times this one by 5 and this one by 2, we're going to end up with 10 electrons in each, and that will give us a balancing of electrons. So let's do that. So we end up with 5 H2S. Actually, I'm just going to do it here. We'll save time. 5 H2S plus 5S plus 10 electrons plus 10 H plus. This side is going to be 2 plus 16 plus 10. There we go. Electrons are balanced. Plus 2 Mn2 plus 8 waters. Okay, so now we can cancel out these electrons. Now, let's add them all together. So we end up with 5H2S plus 2 MnO4 minus, that's going to be gas, that's going to be aqueous, plus 16H plus, 5 sulfurs, and 2 manganese ions, plus 10 H plus 8 waters. Now we've got 10 H plus here and we've got 16 H plus there, and so we can cancel those out and we end up with 6 H plus. Right, that is the balanced equation. I hope that has helped you with how to work with the standard potentials table and how to read the oxidation reaction, half reaction, and the reduction half reaction. Grade 11s, I hope to see you next time.